Okay, so hello everyone. Welcome to which one? Which lecture is it? 10th? 9th? I think it's 9th. 9th lecture?
Yeah. Yes.
Okay, so last week, what did we do last week? I know where we ended last week. We ended on, so we had dynamical map, which I wrote here, okay? We found out that, we have a dynamical map, complicated problem, issue of computability, how to calculate it, right? And we found out that the method with supercumulant expansion actually works for dynamical maps, which basically will enable us to if we have supercumulant expansion, then we can work on some perturbation theory to actually turn it into a way to compute the dynamical map approximately, but still some way to get some concrete results, right? But I pointed out that previously when we did supercumulant expansion, we used it for stochastic maps where it was used specifically to deal with average over stochastic processes trajectories, right? So here it works, and so supercumulants exist. Okay, they are well-defined objects. So it's does this mean that we are dealing with average also in this case, in the case of a dynamical map? So are we dealing with some quantum average over some quantum distribution and stuff like that? And this partial trace over environment, is this a formal way to implement this average? Is this just something that looks like average, or is this analogy actually valid? Okay, and this is I think as a theoretical physicist, you cannot shrug off this kind of observation. If you see some kind of analogy, you have to explore it. Okay, is it a real analogy, or just a coincidence? Even if you find that it is a coincidence, you probably will still have to explain, okay, why is it a coincidence? Why isn't there no some underlying underlying law or something like that? So it's you see something that looks at you funny, you want to explore what's going on. And this is so today I want to explore this question. Okay, is this quantum average really a thing, or was it just a coincidence? And so to make it a more concrete problem, so to find out if this analogy with averaging is actually apt, is actually correct, well, we would have to answer two distinct things, two distinct questions. One, if it is an average, then what is the distribution we are averaging over when we calculate this partial trace? And the second question, if we manage to identify this distribution, this quantum distribution, whatever it may be, what is the nature, what are the variables this distribution distributes actually? Okay, because with stochastic processes, stochastic maps, we have this average was over this probability distribution on the space of trajectories, right? Representing some influence from classical influence on our system, right? So will there be some kind of analogy here as well? Maybe we'll discover that the environment, quantum environment interacting with a system is actually like stochastic process, or maybe we will discover that it's actually something maybe similar, but actually different. So this is something that has to be explored. So once you set up this problem in this way, that you want to find this distribution and figure out what it distributes, well, to answer this question, inevitably you will have to do some algebra, right? So we will do some calculations along the way to actually figure out what's going on and to satiate our curiosity in this regard. So so to get to the work, to proceed further. So again, we have our dynamical map. On previous lecture, it's defined in this way. So we have this time ordered exponent that it's partially traced with density matrix of the environment, initial density matrix of the environment. So we had some notation convention here that this S times F, this is a shorthand for this longer expression when you have sum over alphas and you have this like product of coupling operators on the side of the system and coupling operators on the side of the environment, right? Time ordering and partial trace. So we will start our adventure, our investigation by taking this exponent and expanding it into series. So you have this suspected average over this whole exponent. So let's turn it into a suspected average that goes term by term. So this is the first simple step. So we'll have identity from the zero order term, and we have a series and goes from 1 to infinity. We have the coupling constants and imaginary I. We have time order integrals as usual because of time ordering. U2, U1. Well, and we have our suspected average partial trace, and we have the argument of the exponent, so the coupling superoperators in the interaction picture. So let me write it like this. So we have S times F time U maybe K. K goes from N to 1. And this guy acts on the 0 E. Okay, so this is just a shorthand for ordered product, because there will be many of those. This kind of notation will be useful. So I have some super operators indexed by time. So this, read it as starts from UN minus 1 and goes to a U1. All right. If the indices were inversed, so we would start from K1 to N, that would mean just inverse the product. Okay, next. So the aim here is to, once we did this expansion, now the aim is to like push as far as possible, try to calculate this partial trace as far as possible and explicitly calculate as far as possible. Okay, so to reduce it to the most bare bone form. Like no more simplifications will be possible after we are done, right? So to carry out this calculation to its bitter end, we'll need like a couple of things, couple of objects, okay, a couple of tricks in our bag. So one thing that we will need is a spectral decomposition of E-side couplings. So those operators F, okay? We want to have their spectral decomposition. So just as a reminder, F, operator F, it was defined, it formally depends on time, because it was defined as a bare coupling operator E shifted by an average value of operator E times 1, which what it actually means is trace over E alpha and U E T0 rho 0 E. Okay, average, well, we are suspecting this trace, partial trace, as a kind of average. So that's why, hence the name for this guy. So because it's defined as this shifted E, so it's for spectral decomposition, we need to solve the eigen problem for operator F. That is to find its eigenvalues and eigenkets, eigenvectors. But because it is just E shifted by identity, something proportional to identity, this means that if we solve eigen problem for E, we automatically solve eigen problem for F, right? So it's determined by the eigenvalues and eigenvectors of this bare operator. So keeping this in mind, now let us recall assignment 11, which was an assignment where we solved it together on the lecture, during the lecture, and it was about this weird group theoretical underpinnings of unitary transformations. If you recall that stuff, there was like, we had this picture that unitary transformations are like points on this hypersphere S of dimension d square minus 1. For example, identity would sit on the pole of the sphere, like operator of this sort. You could visualize it as a like a path on this hypersphere, and if you had operator that's time ordered, has some time ordered Hamiltonian, so you then that would be a path that goes like maybe, it wiggles a bit along the way, and so on and so forth. You remember that? Where like the assignment was to find an interpolation between two unitary transformations, but it was just a pretext to talk about, Lie algebras and SUD group, special unitary group, and stuff like that. But the bottom line from that was that unitary transformations, which you can think of as some basis transformation, can be parametrized by, you can parametrize them using a set of generators and a vector of coordinates, right? So this operators TL, L goes from 1 to d square minus 1. So this would be a Hermitian generators, and this phi is just a vector of coordinates. So a point on the sphere, that would be some phi with an arrow. Right, so any unitary transformation, that is any transformation of any basis transformation, you can write it in this way. Okay, just pick a set of generators, and this would correspond to some point on this hypersphere, and you compute this exponent, and it gives you something that rotates one basis into another. So I want to use this parametrization right now, okay? So we want to find an eigenbasis, so basis made out of eigenvectors of operator E. So that's one thing. The other thing, we have this parametrization of unitary transformations, okay, with a coordinate on this abstract hypersphere. So if we pick an arbitrary basis in E ket space. So let's pick a basis made out of kets indexed with psi. Psi goes from 1 to D, okay? So maybe a weird symbol for indices, but it will look cool, okay? And then to solve the eigen problem, so we have this basis. So finding the basis of eigenvectors of operator E amounts to picking, having this initial reference basis. We just have to state what is the value of these coordinates that executes the transformation from the reference basis to the basis of eigenvectors of E, okay? So solving eigen problem for E amounts to just picking a correct value of this coordinate vector, okay? So in other words, eigen problem for E alpha, it means so we can like write it in the following way: E alpha psi times 1 and psi. Okay, so this means eigenvector, eigenvalue, right? So you if this is eigenvector, this is eigenvalue, then this equation gives you 0. This is how you can like summarize the eigen problem, right? For any operator. And with our parametrization of unitary transformations, we can recast it in the following way: psi 1 E I T. Let's add index E to remind us that these are generators of transformations in ket space of the environment, and times coordinate, and I would denote it as alpha, acting on the element of reference basis. Okay? In other words, coordinate alpha execute transformation that takes a reference vector and converts it into eigenvector of operator E, corresponding to eigenvalue small e. Okay? Maybe complicated so far, but bear with me. Bear with me. There will be a payoff for this weird construction. Maybe not a big payoff, but I really like it. So once we have this alpha alpha vector determined as a solution to the eigen problem. This means that it is also the solution to eigen problem for operator F, as we can simply. So this is this, and we can like add E alpha t, subtract E alpha t So we just add 0 to the whole thing. Right, and we collect minus average E and E. So this will turn into F, right? And E alpha psi minus average value times 1. This turns into the eigenvalue. Right, so this number here, this is what will be the eigenvalue of operator F psi. And it's because this average E depends on time, so formally this eigenvalue is also time dependent, okay? So we have found the we have a solution for eigen problem of operator E, which automatically gives us a solution to eigen problem of F. So now we have a full set of eigen cats. We have eigenvalues. This means that we can now construct the spectral decomposition for F, for operator F. So spectral decomposition. So let's take F in the interaction picture. You know what? Maybe of T, which again from the previous lectures, this means that we take F and sandwich it with F depends on time formally. We sandwich F with unitary evolution operators in E, in environment T. And now we have a spectral, because we solved the eigen problem, we have a spectral decomposition of F. So we can write psi from 1 to D, eigenvalues alpha T psi E I H T E I T times alpha psi and the brass alpha EI minus H E T, okay? And now we can take this operator here. This is let's call it P, that's indexed by T and by coordinates, but space-time coordinates. Okay. And this operator's P, so if you fix the coordinates here, you obtain the whole family of orthogonal, full set of orthogonal projection operators, rank 1 projection operators. So in other words, for any P phi psi defined as EH. You know what? Let's add index E here. Remind us that this guy is made out of Hamiltonian and basis transformations in environment. Psi. Okay, and for any fixed, if you fix T and phi, you get that sum over psi 1 to d of PE T phi psi, you get identity, and you have unipotency, I think this is called, right? I mean, the fact that they are orthogonal. So you take psi, you compose it with other guy, some psi prime, and you get delta psi prime, PE T phi psi, okay? Set of orthogonal projectors. Which if you adjust the coordinates accordingly, you can get a projectors onto eigenstates of given operator, okay? So using the same idea and same notation, we can also spectral decomposition of initial density matrix, right? It's also an operator. There was nothing special about operator F after all. So you can also do the same kind of spectral decomposition for rho, eigenvalues, and the projector. You just have to zero time, and you just have to adjust the angle. How to write the rho? So I want to indicate here. Let me try to show you what kind of font I want to simulate here. Oh, you see this? Var rho. Oh, sorry, I need to show it to. So this is normal rho, and I tried to write this var rho. Okay, so forgive me that if it doesn't look like that, but exactly. But this is what I tried to simulate with the with this wind symbol. Okay. Oof. So hopefully this is it was possible to follow this stuff. We basically chose a kind of weird parameterization for bases to denote bases, right? And I like this parameterization because it's like it's like the choice. I mean, time and observable, it's like, the part of one set of coordinates, right? You have time, Hamiltonian generates boosts in time, and the changes in observable you are looking at is like has space coordinates that are generated by this operators T, right? So you have this one big space-time coordinate that gives you choose time and choose observable. Okay, so I kind of like it. It's like it's very compact way of looking at this stuff. And now, so we have this toy in our hands, and now we can use it because again, what I want to do, I want to take this expression. So this is a product of a bunch of super operators. There is a density matrix here, and this is partial trace. I want to calculate this partial trace as far as possible, okay? So now I introduce the spectral decomposition for operators in environment, right? In thinking that it will help me in doing this calculation. And now I want to use this spectral decomposition to show use spectral decomp to show that this interaction super operator, these guys that we are dealing with, okay, to show that these guys they factorize into S part and E part. Okay, factorize in the sense that outer product factorization. Because if we can show that, then the composition of them will also factorize, and if we have some super operator in S times outer product with super operator in E, then doing a partial trace is much simpler to do, because you just partial trace cares only of what happens in the environment, right? So let me show you what I mean by this factorization. Maybe technically it's not the correct word to use, but you will see what I mean when I write it down. So let's take one of those guys, F interaction picture. So we have this guy, this adjoint super operator, and let's just use the spectral decompositions that we just obtained. So this guy, translating this shorthand notation into a sum over alphas, okay, and this is alpha. So what do we have here? So we will have operator S in interaction picture times operator F in interaction picture. They act. There is a bullet here, right? The argument minus this, and you act. Let me write it like this. Keep the parentheses in check. F alpha U. Okay. So I just unraveled this shorthand here. And now sum over alphas. Okay, sum over alphas. And parentheses. So we can write it as U bullet times. Let's put here spectral decomposition. F alpha U psi plus P E U alpha psi plus bullet. So this is, I unraveled this first term, and we have minus SU alpha times bullet sum psi minus F alpha U psi minus P E U alpha psi minus. Okay, so this is this second term. And now let me pull out all the sums before I pull out sums. let us notice that here is bullet, but I can always insert here identity, right? If nothing stops me by multiplying this with identity. And also I can insert identity here. Nothing stops me, right? But identities have this property that they can be decomposed into projection operators, right? That's a cool trick. So let me change the color for a bit. So this identity here, I can write it as sum over psi minus PE U alpha psi minus. Okay, and this guy here, I can write it as a sum over psi plus PE U alpha psi plus. Nothing stops me from that. This is algebraically, this is all correct. So having said that, now we can pull out all the sums, sum over alpha, sum over psi plus and minus, goes from 1 to d. And we get the following. F alpha u psi plus S alpha u bullet minus bullet S alpha u F alpha t psi minus times PE u alpha psi plus bullet PE u alpha, oh my, I ran out of room, of psi minus. Okay, I hope it's you see what's going on. So I just pull out the sums, this sum and this sum, this sum and this sum. That's why everything is summed over psi plus minus. And it happens that in this term, psi plus goes over projectors, yes, but also over eigenvalues, right? So that's why we have this guy here. In this term, psi plus goes only over projectors, but psi minus goes also over eigenvalues. So you get this. These are numbers, right? So we have a super operator in S times super operator in E. This is what I meant by this factorization. All right? Okay, we're almost there. We're almost there, almost there, almost there. So now we can come back to coming back to dynamical map. So we have our UT0, right, which was decomposed into this series, right? And now we have this additional level of decomposition for those super operators here. So we can just plug it in. We will get a product of something that is in S, outer product, something that is in E, and the trace cares only about the stuff on E. So let me write what we get. Yes.
Just a little bit
Earlier.
That's on the last version of the
Later in the sense. Okay, later in the sense of this normal chronology.
Really less empty space at the down over because And that's usually not.
Ah, you see, okay, sorry. I went too fast. Okay. Sorry. Let me gather my thoughts, what I want to say here. Okay, this and this. Okay, good. Very good. I had time to check the notes. So minus I lambda n. We have the time ordered integrals. We are almost there. U2 du1. Okay. Now I will collect the sums. So we'll have sum over alphas. So I will use our tuple notation because there will be for every instance of this adjoint superoperator, there will be sum over alpha. So there will be n alphas here. So I use our tuples. And we will have sum over also a tuple of psi's, plus and minus, actually a pair of tuples. Those are those sums here. Okay. And then times. So we will have a piece. So I will use my shorthand with product. K going from n to 1. So we'll have a piece that acts in S. So the composition of those guys, basically. So open parenthesis F alpha K U K psi plus K S alpha K U K bullet minus bullet S alpha K U K F alpha K U K, a lot of indices, but this cannot be helped. Psi K. So this is the S part. Then it should be a light bulb with the E part, but there is also a partial trace over E, right? So we can turn light bulb into just multiplication over numbers, because trace turns everything into numbers. So we'll have times sum over additional psi 0. It will be, I will reveal soon where it came from. Trace over E. So this is the trace. And we have a product. K goes from n to 1. P, E, U, K, alpha K. Okay. Psi plus K. Then in the middle, I will reveal what's in the middle in a second. Because look, what these guys do, they are sandwiching, right? You take something, you sandwich with two projectors, then so this is the action of single this adjoint superoperator. Now the other adjoint superoperators comes in. What it does, well, it takes this sandwich and sandwiches again, right? And then again. So we will accrue a sandwich that is like the bread, which is made out of those projectors, is just getting thicker and thicker. Okay, so this is this bread of the sandwich. It got thicker and thicker, and you have the other side of the sandwich, which is also the bread. You also have projectors, but they go in the reverse order, right? Because you sandwich from the middle to the edges. So here K goes from 1 to n, okay? PE UK alpha K vector, and they depend on psi minus. All right, so this is what trace. And now what's in the middle? Where in the middle, because all those S guys, let me jump here. So we have a product of S guys, and they act on the environment side. There is a initial density matrix. This whole sandwich with thick bread slices on both sides, the meat inside is the density matrix. Okay, so the thing in the middle here, this should be a density matrix. This should be density matrix here, but we have a spectral decomposition for this guy, right? So I can replace it with sum over psi zero, projector E0, this var rho here, psi zero, okay, and pull out and the eigenvalues. Psi zero, okay. So using spectral decomposition, we get this. We can essentially replace the. We can make the density matrix fit the rest of the sandwich. Okay, meat is also a projector, but this projector with a depends on phi zero. This is this phi zero, zero time, and this angle coordinate chosen in such a way that you get a transformation to the eigenbasis of the density matrix, and you get this distribution hanging around. No, we can just take it and pull it, let's say, into the back, right? We can just write it here, psi zero, if we want. Okay, so in other words, so let me introduce symbols. And hopefully this explanation is clear what maths was done here. So we have our stuff here, all the integrals and all the sums, UN 0, U2, du1. We have a sum over alphas tuple. We have sum over psi's tuple, and we have a product. Well, also a sum over psi zero. Let's pull it out here. And we have a product of those super operators in S. Okay, UK bullet S alpha K UK F alpha K UK psi minus K. Whoop. And this trace of this sandwich of projectors, I will call it Q index E, because everything inside is associated with the environment. And let me index this guy with tuple of coordinates. Conditioned on zero time and the coordinate of density matrix that depends on the sequence of psi's, psi plus and minus. God damn it! Can I move it somehow? Okay, I don't know how to move it, and I want to use the notation that's reminiscent of conditional probabilities. Okay, so vertical bar and squeeze here psi zero, if you can. Okay, and in front of everything, we also have rho E psi 0, the eigenvalues of the density matrix. So in other words, we took this trace with projection operator from the density matrix. So it has this whole sequence of space times coordinates, right? Indices everything. And I call this trace Q. Okay, and I keep the information about indices and I keep information about the arguments for the projectors. Okay, so where did this lead us? So I want to bring to your attention, I want to make a comparison here. Because remember, we are doing this because we want to identify if this partial trace is an average, some kind of average, then there is this distribution that we are averaging over. So I want to identify what this distribution could be, okay? So at the moment we did some weird algebra and we found this family of functions Q, complex valued functions Q. So now let's compare this compared to stochastic maps. Right? Because the idea of average, we got here by considering an analogy to stochastic average, right? So if we take the stochastic map, which, just to remind you what kind of maps we used, there was time ordering, of course. There was an integral here. There was a stochastic process F, coupling operator V, du, and everything was averaged. Couple of lectures, couple of weeks ago, we looked at these kinds of objects. And now if we expand this exponent into a series, if we expand this guy into a series, we will get, we get our integrals, of course. We'll get sum over sequence of n's. We'll get product, k goes n to 1, of super operators in S, like fk, v, uk. So we get the product and we get a distribution. U F F. If you remember the stuff. So this was like a multi-time probability, joint probability distribution for the sequence of values of the process, right? So if you compare those two guys, right, by analogy, I will identify those functions Q as the distributions we're looking for, okay? Because they appear in a similar place as probability distributions P appeared previously. So, you know, if this is averaging, then this surely looks similar to averaging. So this will be my identification. So we found our distributions. So we have a function. No, I probably will need all the room I have. So we have a function that takes two sequences of indices, psi plus and psi minus, two tuples, and sends it to QE, which is indexed by times and angles, conditioned on some zero row, whatever, psi plus and psi and minus, conditions on psi zero. Okay, so we have those guys, and this is in general complex valued, right? If you look, this Q is at this trace. Okay, so this in general is a complex number. Cannot guarantee that it's real. Okay, and now a couple of things. So since this guy is complex value, so it's not probability distribution, but it is a distribution. Doesn't have to be a probability distribution to be a distribution in a sense of measure theory. And it depends on the pair of sequences rather than on one sequence, rather than on uni-sequence. So this is like a B sequence. Let's call it B sequence, sequence. And this would be a uni-sequence. Sequence, just to have some way of speaking of them in shorthand. So this is a complex value distribution that takes B sequence as a argument, okay? So I will pick a name for these guys, and that name will be by probability distribution. So we have a name for it now. It's by probability distribution. And before we go to break, one more observation, because we are not done yet, unfortunately. Because, okay, so we have those by probability distributions, which are somehow analogous to those multi-time probability distributions for uni sequences, okay? But we know from stochastic processes that such a multi-time joint distribution is but a discrete time restriction of a master distribution over whole trajectories, right? So this is the master distribution of trajectories, of uni trajectories, at least uni trajectories. So we have whole trajectories here, right? And now, if these bi-probabilities are analogous to these multi-time joint probabilities, is this analogy really full, really complete? And there are also just like those guys, those are also some discrete restrictions of some master by probability distribution that would be analogous to this guy, okay? So if this is analogous to this, is there a thing that's analogous to this? So the plot thickens. And now let's take a couple of minutes of break before we answer that burning question. All right. Panie Kubo, jest pan?
Jestem.
Okay. Okay, so let's continue. So is there must there be probability distribution? That is our question now. Okay, so we're moving to next section. It's a bombastic title, B-trajectory formalism for quantum mechanics. So by probability distributions, we discovered them by inspecting a dynamical map, right? And it's clear from their definition that those distributions Q, where's the definition here? They are evidently associated with the environment, right? Because they are made out of things that pertain only to the environment, right? So they are like something that characterizes the environment, right? But if someone just sends us via email some quantum system, some arbitrary quantum system, and just gives us, okay, this quantum system have this Hamiltonian. This is what generates dynamics in this system. Then there is some Hilbert space of cats for this system. So we can always pick some basis, this psi in this system they send us, and we've picked the reference basis. We can always pick the generators of transformations, right? And we have those three components that we can define easily for this hypothetical system, a family of projectors, right, made out of those building blocks they gave us, or we stumbled upon, right? There is just this formula is kind of universal in this sense. And if we have projectors, now we can use them to generate by probabilities that will be associated only with this system characterized by this Hamiltonian. Okay. So given those projectors, we can generate a K and it's to 0 actually, not to 1 but to 0. P tau K psi plus K. I'll explain myself what the tau means here. As imagine is another shorthand. So tau, when it's appropriate and it's clear from context, tau is just, it's just some t and some phi, okay? Just a shorthand, not to write everything outside. So notice that this product goes to 0, okay, not to 1 as previously. Well, we can accomplish this trick because once we reach tau 0, psi 0 plus from this guy, right? There will be something in this guy, and here we start from tau 0, psi minus 0, right? And stuff goes here. But these are projection operators, right? They are orthogonal. So this is just delta psi 0, psi minus, p tau 0, psi, say plus 0. So this is what you can. So the middle of the sandwich that was we used to like make a connection with the initial condition, the density matrix. In this by probability, it was came in as a the middle one projector, right? But it's a projector, so you can always split it in two. And just to for the sake of symmetry, you can like get this handsome formula. It's kind of maybe spurious to split it into two, but it just underlines that you have those two sequences, the plus sequence and the minus sequence. And this just tells you that those sequences, they have this property that they form like a closed loop, I guess, because they start from the same point, because in the middle, because of this in the middle, and on the end points, you have p tau n on the right side, but the trace is cyclic, right? So they also meet, and they also gives you another delta. So you have this sequence of psi pluses, psi minuses, but they start from the same point and finish at the same point. Just a curiosity about this stuff. But the fact that whenever someone emails us Hamiltonian, we can generate those by probabilities, which they are then associated with this system, this quantum system, with this Hamiltonian H. This means that you can also take those by probabilities and abstract them from this narrow context of open systems and environments. And as a matter of fact, there is a way to like create the whole formalism for quantum mechanics based on this construction. So this this is what I mean, this bi-trajectory formalism, where those distributions, like you use those distributions instead of states. You would normally want to use in the standard formalism for quantum mechanics. So this is like another way to think about quantum mechanics. It's kind of like with classical mechanics, you have your Newton equation, Newton formalism, but you also have Hamilton formalism, right? Different way of describing the same theory, using different objects. Here forces, here you have some Hamilton functions, whatever. So there is a way to use those by probabilities to actually create an alternative formalism for quantum mechanics, the whole quantum mechanics. And here we will, in this course, we will touch upon this at some point and some aspects of this whole idea. If you want to know more about this, there is a lecture I gave previous semester that is only about this idea, okay, about this alternative formalism. So you can find it on YouTube, recorded stuff, if you are interested in this. But
will it be done in future years?
Done in what?
In some close future, you will be doing it like as a course.
There is course about this. It already happened in previous semester, and it's all recorded on the YouTube channel.
Okay.
So you can if you go to the website, you can find the links. So if you want, you can watch the whole thing, and so yeah, so there is a reference to that. Okay, so I won't go into details because as you can imagine, going all explain everything, you need like 30 hours to do it. So this is like here it's kind of a side note, interesting side note, but side note nonetheless. But now, if you consider these objects, this by probabilities in this new context of formalisms, then this question of existence of this master distribution becomes like more of a fundamental problem. Because if you believe me that you can build this formalism, then this family of those by probabilities indexed by these sequences of coordinates, they provide the holistic description of a quantum system. Okay, so now if you can show that those guys are but some restriction of this master object of something analogous to this, then this master object would be like the real source of everything, the real master object of the whole theory, right? So it's very interesting to see if it can be found, it actually exists, because then it will supersede everything else in the formalism, essentially. Okay, so having in mind those stakes, those new stakes, so ultimately the question whether this analogous master distribution exists is a mathematical question, okay? Because so to like express it in more technical ways, more technical terms, so that the mathematics would require from you to show that you can take those by probability distributions and that it is possible to take a sensible limit where you like take those coordinates, the sequences of coordinates, and make them infinitely dense. Okay, so it's not just a sequence, time and coordinate like this, but it's actually it becomes like the whole area set. And if this limit exists, then this bi-sequence of psi plus and psi minus would turn into bi-trajectory or bi-trajectory. So this is like similar thing that happens here. So this is like a multi-time probability distribution defined on like a discrete grid of times. And to obtain this guy, you can imagine that you take a limit where this grid becomes denser and denser and denser until it's like full interval of time. And then sequences becomes functions of time, right? So you want to do something similar here. You want to show that this exists and makes sense. And this is, so basically you want to prove a generalization of so-called Kolmogorov extension theorem. Kolmogorov extension theorem takes care of stochastic processes for probabilities. It works for probabilities, and you want to extend it or generalize it to bi-probabilities. And we won't be doing this here, okay? Because this is a big and quite complicated problem, and the state of affairs at the moment is that we have proven we have a partial result, okay, that this limit exists, but in certain circumstances. We at the moment don't really have the full constructive proof that shows this, how to make this limit work in this full generalized case, but we have an indirect arguments that support that this. Maybe we don't exactly know the mechanism behind this limit, but we can show that it exists. Okay, that it can be made. We maybe don't know how it looks exactly, but we know that it can be made. Okay, something like this. So this is still, in a sense, this is a still open mathematical problem. If someone's interested, it would be cool if it could be closed. Full proof would be available. I would really love to see that. But given that we have this indirect arguments and they are pretty strong, I can say with high degree of confidence that this is actually true, that this Q by probability, something like this, okay, that is actually is a discrete restriction of a more fundamental object. It is a very interesting problem. It is a very interesting problem, mathematically and physically. So restriction in the following sense, psi k, psi plus of tau k, the second delta, psi minus tau k, and there is this master distribution. I always run out of space to write everything. So there's a double integral, double functional integral over psi plus and psi minus. So this Q, this functional, okay, so this is let's say this is master distribution, maybe master by trajectory distribution. By trajectory distribution. It is complex valued, okay? It is complex valued. So it's not a probability distribution. And it's a measure, so it's a complex value measure on the space of by trajectories. B trajectory. By trajectory is so is a pair of functions, pair of trajectories. Tau. So tau, the arguments, you take them, there is a time component, so it's a real number plus a coordinate on hypersphere, right? So tau is some t and some phi, okay? And the values, well, in this parameterization, we're using these trajectories take on discrete values. So it goes from 1 to d, but it's a pair. So it's a pair of numbers, discrete numbers, where d is the dimension of the space, of this quantum system, all this stuff is associated with and describes, and what describes. So now that we are aware of the existence of this master distribution, okay, we can finally answer our initial question, right? Is this partial trace really a average, some kind of average? We can, if we have this relation here, we can use it that indeed partial trace is average and is an average over by trajectory with this distribution, this master distribution Q, okay? So in particular, if it's a distribution of by trajectory over by probability distribution, it is not an average over uni trajectory of a master probability on space of uni trajectories. So it's definitely not, this quantum environment is definitely not a stochastic process, okay? It's something else. It's this by process. I don't know if you want to call it like that. So let me show that it is indeed this average. And this is like basic trick at this point. So we have our series. u2 du1. We have our sums over tuple of alphas. We have sum over n tuple of psi's. And we have also a sum over psi0, to have the information about initial condition. But I will also, just for the sake of symmetry, I will make it a sum over psi0 plus minus, and I will just put here delta to facilitate it. Okay, this delta, you can think of it as the thing that actually comes from the properties, basic properties of biprobabilities, right? This looping of the by sequences. And once we have this, we continue writing. So we have a product of superoperators, alpha k, uk, psi k plus, s, alpha k, uk, bullet minus bullet, uk, alpha k, f, alpha k, uk, psi minus k. It's a mouthful. There is a density the eigenvalues of the density matrix, because it's a eigenvalues of density matrix are non-negative because it is a density matrix. One of the properties is that it's non-negative. So I can calculate the square root of them. So again, for the sake of symmetry, I will split my eigenvalue of density matrix into product of square roots. Okay, I'm just making it more symmetrical. And finally, we had the biprobability distributions here. Q, E, that we had here. We had here whole indices, row index, right? Psi plus n, psi n minus, psi 0 plus, psi 0 minus, okay? But now, we have this. We have this equality. So we can replace this discrete biprobability with this integral with deltas. Okay. So let me like cross this guy out. So let me cross this guy out and replace it with double integral. We have a product. Okay, goes from 1 to n. We have delta psi k plus psi plus at time uk alpha coordinate alpha k. And we have this for the other sequence, the other component of bitrajectory, uk alpha k. Okay, and we also have to take care of the initial condition. So you have psi 0 plus, psi plus 0 row, psi 0 minus, psi minus 0 row, times the master distribution. All right. And now we simply exchange the order of sums with integrals. So we take those sums over psi's, jump here to the deltas, evaluate deltas, and basically exchange sums with integral. So if we do that, the sum over n 1 to infinity minus I alpha n integrals E1 let's leave alpha for now. Do we want to leave alpha for now? No, I don't want to leave alpha for now. I want to be more tricky about this. So scratch that. Scratch that.
Why this dot and then minus? No, wasn't there plus at the beginning?
Plus. Here is the plus. Here's the other part of the plus. Okay. Plus. Yeah, sorry about that. So we have this double integral over b trajectory, and let me see what do we have here. So we'll have a product. So the super operators in S. Okay. So we have a product here. We open parentheses. Each one will be summed over its alphas. No, parentheses here. So F alpha K U K psi plus, but here it was an index, right? Which we using the deltas and sums and integrals, we basically exchange the value of index for the value of bitrajectory. Okay. So we have a value of bitrajectory evaluated at time UK and coordinate alpha K. Boom. Alpha K UK, bullet minus bullet, S alpha K UK, F alpha K UK. A lot of indices. Sorry about that, but can be helped. And we have the other component of bitrajectory evaluated at the same space-time point. Let's call it space-time point. So these are the super operators. So what is left? We have two pieces left. One is the initial condition, which again index is transmuted into a value of the b trajectory. That's why it's useful to have this weird symmetry with square root. And finally, we have our master distribution of the b trajectory itself, plus b minus. And now we can start to compactify this stuff. So first thing first. So here we have we can take this integral and actually pull it before every other time integral and sum. That's okay. This is what we define for us the average. And so if we do that, then we have this time-ordered product of super operators, right? So we can pack it back into the exponent. Okay, so let's start with that. So we have a double integral. There will be time-ordered exponent. The ordering we go. So I introduce new super operator Z, just to be annoying. But it's for the greater good. Don't fret. Z, super operator Z, it's time dependent, but it also depends on bitrajectory integrated over U. I will define Z in a second. Then we are left with initial condition here, psi minus rho square root, and finally times the distribution. Psi minus. So maybe I should write here a quick, so that defines Z. And one more thing, this whole integral with this initial condition and this distribution, let's give it a symbol as well. And I'm explaining the notation. Is U psi minus du. Okay, so this, and now explaining notation. I leave it on the screen, right? So to give you a chance to take notes. Notation explain. So thing number one, Z. What is Z? ZT psi plus psi minus is merely sum over alpha f alpha t psi plus evaluated at point t alpha alpha f alpha t psi minus evaluated at point t alpha. So in other words, those guys, okay? So this is these super operators. So just name them Z, okay? And I will refer to this guy as a dynamical variable. Dynamical variable. Just to have a name for it. So it is a super operator in S, okay? But it also introduces the dependence on bitrajectory, the whole expression. This dependence comes through those eigenvalues here, right? And it depends on bitrajectory by evaluating it at this given space-time point, okay? But it's this thing will just drag along everywhere with us. So the other thing, we have this average, symbol for average. So x psi plus psi minus. This is just double integral of this x psi plus psi minus. This weirdo initial condition and call that in eigenvalues of density matrix and the coordinates, square root and q psi plus psi minus. And psi minus. All right. So this will be our average over B trajectory or bi-average or whatever else you want to call it. So this is ultimately answers our initial question. Is this partial trace an average? Yes, it is. What is it average over? It is an average over this bi-probability, bi-trajectory distribution. What is the nature of variables that are average? Well, the bi-trajectory, which is like an next evolution, well, next step over unit trajectories we know from stochastic processes. So this makes it explicitly like, quantum problem, because it's described in terms of bi-trajectories, not in terms of unit trajectories, as it was case with stochastic maps. So if you allow, give me 5 more minutes, if you will be so kind. I want to say one more quick thing, because this analogy with average works very well, and as it turns out, as you can see, right? Those expressions all make sense. This is an average, this is a distribution, and it's very surprising that it doesn't really bother. It doesn't matter very much that this distribution is not a probability distribution because it's complex value, right? So we could expect that should be so much different than standard averages over stochastic processes or stuff like that. But as it turns out, if you look at the structure of this average exponent and compare it to what happens with analogous average with stochastic processes, basically things go in parallel to the point that you can also have cumulants with bitrajectories. Okay, so if you use an analogous, so cumulants, if you use an analogous definition to what we had with analogous definition of cumulants to what we use for stochastic maps, so we had our minus I lambda 0t zu psi plus psi minus, and you say, you know what, I want to absorb this average inside the exponent, and you say, okay, so let me make an implicit definition where I introduce the thing I will call the cumulant, and I introduce cumulants un z u1. Okay, so this would be cumulants, right? This is analogous stuff we did with stochastic maps, and this thing works, and this analogy is so I would say perfect that what this definition, because it's a well-formed definition, that is you can find explicit value of cumulants doing the standard procedure with expanding both sides and comparing orders and stuff like that. But it will lead you to the conclusion that you also have this moment factorization pattern that we observed with standard cumulants. That is, this stuff is actually equivalent to saying that if I take a moment, z tn, z t1, so that would be a moment of dynamical variables. It actually turns out that it equals to sum over p belonging to pairs, not pairs, sorry, partitions, partitions of set into one, times, if you recall this formula, z t pk. So if you compare it to p1, so this is p's, capital P's are partitions of a set of n indices into sequences, right? And small p's tuples are those sequences, right? And you take a product over cumulants, but there's one more wrinkle here, because those dynamical variables are superoperators, so their placement in the sequence matters because they don't commute. So you have to augment this whole thing with time ordering. Okay, and now if you take this and compare it with the cumulants, the various definitions of cumulants for stochastic processes, you will see that there is a one-to-one correspondence, essentially. And to finish this off, the assignment for you. I give you an assignment. Assignment 31. Okay. Find the explicit form of the first two moments and cumulants of dynamical variable z. Okay, so just do the calculations and you know, try them out. Maybe we'll start next lecture by reviewing this or something. And my 5 minutes are up, and we are done. Okay.